everyone. My name is Masum Thakkar. I am a graduate student at University of Maryland in Masters of Robotics. So this is my final review for the course ENPM701 Autonomous Robotics. So in this year's Grand Challenge, the arena was around 10 by 10 feet and the landing zone was around 2 by 2 feet, as you can see on the screen. So the task was to transport 9 blocks which were randomly placed in the cluttered environment one by one in the construction zone. The construction zone was around 4 by 4 feet. So the tricky part is that the blocks were randomized for each turn and we had to transport them in a particular order, which was red, green and then blue. In the first week of the course, we started by learning about the Raspberry Pi, the main building block of this robot. So we learned about its history, its different modules, and also its role in the autonomous system. After that, we started with the hardware assembly, in which we connected the camera module, also the SD card, to the Raspberry Pi. After that, we established a VNC connection to the Raspberry Pi to control it remotely. In the second week, we learned about different kinds of sensor. This robot contains around 4 sensors: camera, ultrasonic sensor, IMU, and the encoders. We also learned about active and passive sensors in this week. In the following week, we learned about the GPIO pins of the Raspberry Pi, and with that, we created our first circuit for this course, which was to detect the distance from the object using ultrasonic sensor. This circuit contained of breadboard, resistor, and HC-SR04 ultrasonic sensor. We connected them to the Raspberry Pi's GPIO pins. We then used a Python script to trigger the sensor, capture the echo signals, and then calculate the time of flight to calculate the actual distance. Next, we moved on to one of the most exciting parts of the course, assembling our ground robot. We started with a robot kit that included motors, wheels, a chassis, encoders, and a Raspberry Pi. Using standoffs, zip ties, and a soldering iron, we built the robot step by step. After the mechanical build, we focused on wiring the robot, connecting the H-bridge motor driver, encoders, and ultrasonic sensor to the Raspberry Pi using GPIO pins. Then came the motor control section. We wrote Python scripts to send signals to the H-bridge, enabling us to control the robot's direction using digital high and low signals for each motor. We first tested basic commands like forward, reverse, pivot left, and pivot right. Finally, we implemented a teleportation loop where the robot could take the real-time keyboard inputs to control motion, giving us manual control over the robot's movement. In the assignment 3 of this course, we built our object tracker on the Raspberry Pi using OpenCV. We captured an image of the traffic light schematic and used HSV masking to isolate the green light by defining precise color bounds. With contour detection, we drew a bounding box and marked the object center. Then we extended this logic to a live Pi camera feed, where our script continuously tracked the green light. Next up, we assembled a servo-powered gripper and mounted it onto our robot's frame. We learned how to control the servo using PWM signals from the Raspberry Pi, adjusting the duty cycle to open and close the gripper. The duty cycle to close the gripper was around 3 and to open the gripper was around 11 for me. In assignment 4, we took our object detection skills further by identifying and tracking a green arrow to estimate its orientation. First, we captured an image of the arrow and used HSV masking to isolate it. We refined the mask with Gaussian blur and applied corner detection to identify the arrow's corners. Using the detected feature, we wrote logic to determine if the arrow was pointing up, down, left, or right in the image frame. Next up, we explored motor encoders, learning how they convert wheel motion into digital pulses. This pulses or encoder takes let us track how far and how fast the robot has traveled. We studied both relative encoders and quadrature encoders and calculated how many motor revolution and encoder ticks are needed to drive the robot based on wheel diameter and gear ratio. Next, we learned how to integrate the BNO055 IMU for orientation sensing, a key step toward real-time localization. The BNO055 combines an accelerometer, gyroscope, and magnetometer and runs onboard sensor fusion to output clean orientation data. We mounted the IMU on a breadboard with an Arduino Nano, soldered the header pins, and connected it via I2C. The Nano sent orientation data over USB to the Raspberry Pi. In the Grand Challenge, we had to send a confirmation email for each block delivery. For that, I configured my Raspberry Pi to use the SSMTP and mail utils. I also set up a Google account with app password access and then wrote a Python script to attach an image block delivery image to the mail and sent it to the desired user. For the Grand Challenge, I developed a script in which the encoder IMU class runs in a separate process to monitor wheel encoders and continuously updates orientation readings from the IMU. At the start of each cycle, the robot opens the gripper and searches for the next target block color in the sequence. It uses HSV masking and contour detection to find the largest object of the color. Once found, it pivots to align using the pixel offset to angle conversion and moves forward until the block is close enough. After the block is grasped, the robot reverses, rotates to face 180 degrees, and navigates to the construction zone using ultrasonic measurements. Then it pivots again and releases the block.